welcome to the video. Today we are going to extend our series on probability theory in coin tosses further, and we'll be touching on probability density function and probability mass functions. So before we begin, one question. What is the probability of getting one head in two tosses? It will be half, 50%. Okay. Then what is the probability of getting 5 heads in 10 tosses? It will be 25%. What is the probability of getting 500 heads in 1000 tosses? The exact 500 heads. The probability is 2.5%. And what is the probability of getting 5000 heads exactly in 10,000 tosses? It is less than 1%. Okay. So this is all happening because of the distribution of the number of outcomes that are being generated when we toss the coins. So this I have explained in my previous video also, but let's touch it again here. So let's say if there is a coin toss, one coin toss, the outcome space is heads and tails, right? Let's chart it on our graph. So this is the frequency, this is heads and this is tails, and this is the frequency or counts. Okay, so this is 1. Now this is a bar graph. Why is this a bar graph? Because we have two different variables here, discrete variables. We cannot connect these two. There is no half head and half toss combined, right? So either it is head or it is toss. So generally we have, for continuous variables, we have histograms is what we say. But we have, sometimes histograms are also used for discrete variables, but which are in order. But bar graphs is generally used for discrete values. Okay. So now from here, this looks like very uniform. Now let's do 2 coin tosses. So our outcomes are head, tail, head, and tail. So now how do we represent this? Head, tails, tail, heads, and tails. This will become, if we have to put it on a bar graph, it will look like we have to have 4 bars because of 4 different values. One will be head, one will be head tail, the other third will be tail head, and the fourth will be tails, right? Instead of that, is there an easy way where we can plot this without going into a bar graph where everything is just being very equal? Instead of that, can we look at certain pattern? What pattern generally we observe when we do a coin flip? We can ask what is the number of heads, right? What is the number of heads? That can be one of the questions. If that is so, then let's go back to this one coin toss. How we can change it to ask this question? What is our number of heads? So we can change it like this, that we can say that there are two quantities, one is 0 and one is 1, and the count here is again 1. So this is the count, and these are the number of heads, the results. Okay. So we have one count of 0 heads and one count of 1 heads in one coin toss. Again, so this is one toss. Okay, now for two coin tosses, similarly we can make a bar graph like this, where we can have 0, 1 and 2. So either we will have 0 heads, 1 heads and 2 heads. So there is one count where we can have 0 head. There are two counts where we can have 1 head, and one count where we can have 2 heads. So this is again count, and this is 2, this is 1, and this is again the number of heads. Okay. Now let's take this further. What do you think, what has happened here? So if we look at, uh, let's take the center point. So we see that there is some kind of a pattern that is starting to emerge. If we extend it further, we will have, let's say if there are hundreds of heads, hundreds of coin flips, 100 coin flips. So we will have one here, a little bit high, a little bit high, a little bit high, a little bit high, little bit high, and there will be one highest peak, and then it will all again die out. By the time it reaches 100, and this is the count. Okay, so what has happened here is we have seen that there is a pattern that is emerging, where there is a maximum value which will be roughly around 50 heads for a fair coin. Okay, so it will start to look like this. So this is very close to how we have a probability distribution function. This is not a probability distribution function yet. This is still a probability mass functions. PMFs are currently PMFs, which is mass functions. They are for discrete values. Here we have 0 heads, 1 head, 2 head, 3 head, 4 head, 5, all the way up to 100 heads. Correct? So they are still discrete. But when it grows big and big and big, then they approximately become a density function. Okay. And PDF, which is a probability density function, they are for continuous values, like height, weight, age, something which is continuous, right? Again, okay. So this is not yet done. So this is a count of all of the 100 heads. So if you have to count each of them, the total count is going to be the total number of total counts is equal to 2 to the power n, where n is 100. You might remember from my previous videos that the total count for a coin flip will come out to be 2 to the power of n. Since we have 100 flips, so it becomes 2 to the power 100. Now, how do we change this to a probability function? We have to divide each of these values by 2 to the power of 100. So let's say if this is the number of uh, uh, x, where x is the 100, x is the number of heads, this is a 50 here, x is number of heads, and this is a count of n of x. So these are all counts. Now we have to divide it by 2 to the power of 10. So this will then become your probability function, probability mass function, f of x. Okay. So this f of x for a probability mass function, it will look like it's a summation where x goes from 0 to some value of n. For here, like here it is 100. Then your f of x times delta x. Delta x is actually 1 in all these cases. So this value is actually 1 for all these cases. So all these probabilities, when you add up everything, this will all come out to be 1. So that is therefore probability mass function. Similarly, let me erase here. For a PDF probability density function, similarly we have a f of x, where x is continuous now. It will look like, I always draw this because this is one of the most common or distribution, which is called normal distribution also, which uh, happens in nature. So this is f of x. This is a probability distribution function. Sorry, probability density function, and this is its most likely value, which is denoted by mu, which is the mean. And then there is a spread, which is denoted by sigma, which is the standard deviation or spread. So this is a probability density function with a mu, which is centered around the peak is around mu, which is a mean, and there is the sigma is the spread or standard deviation that it talks about. Okay. Now here you can see that there is a window for every point. Like just let's say this is the point, then it has a plus minus, it has a delta x to it. Okay. Here there is no window, it's all continuous. So every point is unique on its own. So while in the probability mass function, we can pick any value and then find the probability of that through this, summation, or through this individual probability, or in coin toss, we know that we have seen Pascal's triangle. This will give us each of these different values for different coin flips, different number of coin flips. But for probability density function, this is there to give us a probability only by area. What it means is I have to tell it two numbers that I want to get the probability between x1 and x2. Then only it will give me the probability. Any individual point x1 or x2 or mu or any xyz points on this mean axis, in this axis, the probability itself is 0 for any individual, is close to 0 or almost like 0 only. because here also the requirement is from negative infinity to positive infinity, your fx dx should be equal to 1. From negative infinity to positive infinity, fx dx integral from negative infinity to positive is should be equal to 1. So if you think about this value of fx by itself, it doesn't really signify anything important, except that it you have to get a delta x, or basically two different x's between which it will give the probability, right? This can be anything, but by itself it doesn't give you any meaning or any specific value. When I say mu, and if it's this is fx, whatever is the value of fx, that doesn't mean anything, right? It doesn't give us any information. The information that it gives us is when we compare either less than mu, meaning anything which is on the left side, or greater than mu, which is everything on the right side from mu to positive infinity, or we just give it two values, x1, x2, and then it can give us between these two. So a probability, a small p of x is from x1 to x2 fx dx. So this is the probability of probability between a certain interval 1 to 2. That's what we know from this probability density function. Okay, so this one I told you that this is a normal distribution which is a bell curve, and it is anything which is happening in the nature, or naturally it happens, like a height or a weight or a age, or anything which has a continuous growth or a decline. Area under the curve is what this gives. The area under the curve should be equal to 1. Okay, so that is the probability density function. Now let's take a few examples of what are different probability density functions that we know of. One is a uniform distribution. So here the fx d, and then this is x. This is just one flat value, and then it can go from negative to positive. But all this area, when you do fx dx from 0 to, let's say, n, 0 to n, this should be equal to 1. So this is a uniform distribution. You can think of it as a teacher giving out chocolates to all the students in the class. She'll give out one to each, let's say, right? Or you can think of that anybody who wants something to eat, they can go out and grab a McD burger. Anybody can. It's a uniform distribution. Like there's no control over anything, right? So it's a uniform distribution. Next is, as I said, normal distribution. I already spoke about. So normal distribution is anything happening in the nature or natural. This is the natural growth, or because these are all continuous variables. So a lot of things in the nature that we see, we can attribute to normal distribution. Then there is an exponential distribution. So in exponential distribution, we how it should generally it looks like is it will have a peak and then it will drop. So this is kind of, it starts from 0 and then it can just go on until infinity. So that is the exponential distribution. So where this is applicable is, suppose there is a waiting time in the for a restaurant, let's say a restaurant is waiting for the next customer to arrive. So there is a time at which generally the customers arrive, but as the time increases, the likelihood of customers arriving drops, meaning because the probability of customer arriving at this point is all this, and the likelihood of customer arriving at this point is all this. So as the time goes on, the probability increases much faster. Now we know that probability distribution density function has a mu and has a sigma, which is the mean and the standard deviation for normal distribution. So this is a very interesting concept in higher mathematics, that generally there is the quality of or the confidence level of whether the data is um, between what and what value the most of the data will lie. So generally there are sigma rules that between 1 sigma mu plus minus 1 sigma there is about 67% of the data which lies. Then mu plus minus 2 sigma there is about 95% of the data that lies, and mu plus minus 3 sigma there is 99% of the data which is contained within that. And this is also called 6 sigma uh, for this is used in controlling in quality control. So hope you have got some new information here. Keep watching, keep learning, and hope you like this video.